Okay, thanks. Yeah, and also first of all, I should mention that thank you to Darjeeling Government College for giving me this opportunity to talk. And yeah, so I'll be sharing with you about my own experience in working in a very large collaboration, and perhaps the largest in the world. And we are a lot of people are already aware of what Large Hadron Collider is. So I will be basically sharing my experience with you through these slides, and I will try to motivate you about so that you can pursue a career maybe later in the field of high energy physics. So now moving on to slide number 2. So here, before going into much details about how this collaboration works, I would very briefly want to show you how this machine itself works. So this is the known as the largest man-made machine that has been made on Earth, and I will just quickly show you a video. Yeah, so this is located in Switzerland, and the laboratory is known as CERN, and CERN stands for the European Center for Nuclear Research. And this experiment is known as Large Hadron Collider, and it is basically based on a near to a city called Geneva, and it is in the border of Switzerland and France. And you can see in the right hand side, this is Lake Geneva, and this is Geneva Airport, and this is CERN's main campus. And the whole experimental setup, which is the Large Hadron Collider, which goes 100 meters.
It is not running. Yes, it is running, but interruption is there.
Okay.
It is slowly, I think network problem is there.
I see.
Now we can continue.
Okay.
So let's hope.
Okay. So yeah, so this tunnel is basically 27 kilometers in circumference, and it is 100 meters deep underground, and it is partly shared in the Swiss-French border, and the border goes somewhere from here. And it has main 4 detectors. One is CMS, and just opposite to it there is ATLAS. Then there are 2 other experiments, ALICE and LHCb. So I am mainly a part of CMS, and all these experiments have a little different experimental goals. So now moving on to the next one. Yeah, so now I will just tell you about a very brief history of what happened in 2009. So it was 23rd of November when the first particle collision occurred in all these 4 detectors at LHC. And at that time I was in school. I was reading. I was a student of class 12 back then, and I went to school, and there was a lot of news going around that some people are colliding particles, and it might create a black hole, and that would end up eating the whole planet, and the whole humanity is in stake, and things like that. But one should understand that these type of experiments are done with extreme precautions and extreme measurements, so such accidents are not really supposed to happen. And instead of creating a black hole, what we actually observed is event diagram that I am showing from the very first event at LHC, and this is from the one of the experiments, which is ATLAS, and it is basically, so I won't go into details of this one. It is just showing us the particle tracks in our detectors. So that's when it all started in 2009, and back then I knew a little that I will be a part of this collaboration after 8 years. So now I will show you, so again I will show you a little more about LHC and how this works, because it's very important to understand for us that how this very large vast experiment works, so that to get the essence of why do we need so many people and so many collaborations and so many funding. So it's very important for us to understand how LHC actually works. So let me begin by showing you this video. Yeah. So it all starts from a very small bottle of hydrogen. So we all know that the source of protons are basically, you can basically take hydrogen atom and you can take away the electron molecules, and you get a proton, source of proton. So basically we collide in LHC, we collide protons, and we ionize these hydrogens and we pass it into a LINAC, which is a linear accelerator, and we further boost these protons into a synchrotron booster. So these are different steps when we are accelerating these protons. And then from the proton booster it goes to a bigger ring, which is known as the proton synchrotron, and it is again further boosted in these rings, so it is getting more and more energy in its whole process, and finally when it is energetic enough, it is transported to the SPS, which is the super proton. So these protons are accelerated in the SPS and they are transmitted to the main ring, which is the Large Hadron Collider, and these beams were injected, and then we have detectors like CMS, in which I am a part of, and let me also switch off. Okay, so this is the CMS detector, which stands for the compact muon solenoid, and this collision takes place and it produces a bunch of particles, because these are high energy collisions, and when two protons collide, produces a lot of particles, like order of 1,000 particles in each event. And as I have already mentioned that there are 4 main detectors: CMS, ALICE, ATLAS and LHCb. And now if we take just one of the experiments, say for example ATLAS, and the collision takes place, and from all the outgoing particles we basically get some tracks or some energy deposits in our detectors. So basically by that what I mean is that every particle has some energy and it decays in our detector modules, so it gives us some electrical signal. And now we take all those signals together and we call it a data. And this data is then further processed through a processor and it is sorted, and we only keep those which we require for the further analysis. And each of these collisions are happening for a gap of 25 nanoseconds. So for each 25 nanoseconds we have one collisions. So you can imagine that there is a vast set of data that we are collecting every second or every day. And now finally from all the experiments, all the data are collected and they are sent to a common data center, and where these data are further processed and reconstructed, and then they are made several copies, and finally these copies are stored. So this part is very important to understand. So here in the left we have the raw data, and then we are storing it as a backup. We are storing it in a disk, and for the reconstructed data, a part of it goes to the rest of the world for the analysis, where you analyze the data and perform your physics analysis. And you have for all over the world you have different LHC clusters, where you can simply through your machine you can log into these clusters and you can do your work. So the main reason for me to show this whole thing is is mainly to give you an idea that how complex this whole process is. So you can get the essence that it is very complicated process and it requires manpower. So a lot of people should be involved in such a huge project. So people like from different fields, like scientists, engineers, technicians, firefighters. So by scientists I don't only mean as physicists, so there can be also requirements from chemists or mathematicians, and engineers are definitely needed there to build such large detectors. You need technicians, and also if there is an accident that occurs, so you need firefighters always alert, and you need a lot of funding. So not only a single country can fund for such a large experiment, so you need funding from different countries and from different places. So all this goes towards a great requirement of a great collaborative and management skills. So now I will just give you an example. So this a lot of people has already aware of this famous movie called Avengers. So what basically Avenger is, so they are a team of people who individually has different superpowers, but then some great villain comes one day and no one individually they cannot defeat. So they form a group, a collaborative formation of Avengers. So they all come together. They have different superpowers. Sometimes they are from different planets, even they are from different races, but all of them work in harmony to defeat this villain, and all of them have this common goal to defeat the bad guys in your movie. So that's how we collaborate always, and sometimes there are differences in opinions, and sometimes interests, there are conflicts between interests, so there are fights, and it happens in any big collaboration or any big initiative like this, but mostly people are motivated to work together, and the ultimate motivation is to defeat the bad guys, so, in case of Avengers. And now I will just put up some stats. So if you Google the total number of Avengers there are, and you will find that there are 28 of them. So this number I am putting up in order for you to compare with the enormity of experiment like LHC. So now let's come back to the LHC again. So for the LHC collaboration, we have members, more than 10k members from all parts of the earth, and there are differences in races, ethnicity, political ideology, and there are many more differences between all of us, but we all have one common interest, and that is to do science and to perform experiments. And these are very well motivated scientists who make up to the experiment, and they collaborate together for this one common interest of doing science. And so this is a photograph that I am showing behind you. So this is in the surface of the CMS detector, and here only a few of the scientists are present during this particular photo. So in the next page, I'm just showing you the capacity of the total number of people only in the CMS collaboration. So the blue regions are all the members or the countries who are member of CMS detector, and we have a working number of 2,942 physicists, and among them 1,036 among them are students, including me. There are 1065 engineers, 281 technicians, and there are 229 institutes who are involved in this collaboration. So now I will again come to my own story here. So I started off with this first collision that happened in 2009, and 8 years has passed, and I finally joined CMS in the month of February in 2017. And early days were really challenging. So as soon as you enter to such a big collaboration, you need to understand what are your roles in the collaboration, and how this whole collaboration works, how the detector works, and who are the leaders of your group. And then you have to be very specific about what tasks that you are assigned to, and what are the deadlines of all these tasks that you need to deliver. So I put up a flowchart here in the right hand side to show you how this whole system of CMS works. So this is just one example, and most of the large scale collaborations in field of high energy physics works in the same principle. So if we take only the example of CMS, so at the top level we have one spokesperson who generally speaks for the collaboration. He or she gives away the public results, and she has the ultimate responsibility of delivering any results, or say anything happened to the detector. So she will be the one who is who has the supreme responsibility. And then under her there are several groups. So we operate in this method of forming groups in our collaboration. So mainly we can divide these groups into two. So one is analysis group, another is object group. So I won't go into very details about describing you what exactly are done in these groups, but just in a brief way I can tell you that analysis group are motivated to do physics analysis, and the object group are motivated to create to reconstruct different physics objects from the detector, like the muons, photons, or electrons, candidates like that. So these two groups talk between each other because the object group provides the input for the analysis, and then in the analysis group there are several subgroups. So this analysis group are maintained by these conveners who manages physics results, review results before publication. And in the next step we have these subgroups which are referred here as group 1, 2, 3 and 4. So they have their own sub-conveners, and they will meet with you regularly. They will ask you for updates, results. They will assign you with different tasks. So say now, for example, I am working in group 1 and we have several other members. So for me it's very important to know all the members of my own group, and then it is very important for me to know the sub-conveners of that particular group. And then inside the analysis group it is a little less important for me to know the people who are the conveners, but sometimes every month or so you might need to contact them and asking them for clarifications. And for the object group it is really important for me, and maybe for the other groups who are doing similar physics analysis are also very less important for me, but maybe once in a year you might be stuck into some problem and you need to refer to these other groups, and in that case you can contact them. So we can basically understand that there is a hierarchical structure in this whole collaboration, where there are some leaders and you basically work into these teams and you put up your opinion and ideas. So basically that's kind of motivating you on how these experiments work. Now moving on to the next slide. So here I have prepared a cheat sheet for all of you who are after the discussion of the previous slides, who sort of feels motivated to work in such a large collaboration. So these are few things that I listed out here, which I personally felt that are very, very important for one to work in such a large collaboration. So you should know a lot of people who are working, and you need to talk to people. So you cannot sit alone and do your work individually. So this is a large collaboration. You should understand that, and you should be connected to people over email, Skype or Slack or whatever is the platform that your collaboration uses. You have to check your emails regularly, and preferably in every hour, and except holidays. You have to present your work regularly in the group meetings, and you have to ask questions so that you get recognized more and more. And this is very important thing that I have learned throughout my career, is that once you feel that you are stuck and it is taking away a lot of time, you don't feel hesitate to ask someone. Just ask your questions out, because if the people whom you are asking, if they are available, they will definitely answer you. And if they are not sure about the answers, they will refer to you to someone else who might have an answer. So never feel ashamed of asking questions. That's I think very important for every field. And then there are less important points, like make your travel plans, because you might have to travel to different places for your experimental purposes, and you have to be adaptable and adjustable to different cultures, because you might have to go into some extreme places where you are not very familiar or accustomed to. So you might have to go to those places, and you have to have this adaptable skills. And then you have to be organized, and you have to put reminders, because sometimes it is really confusing with so many meetings and so many agendas. It is very evident that you might get confused. So you need to be organized for that. So now moving on to what are the rewards. So this is very important. So you might be asking that after doing such huge collaboration, spending so much money and time, so what are the rewards that we get after doing such large scale experiments and investing our times and doing collaborations? So we most of us, I think, already know that the rewards of LHC. So since I work for LHC, I will talk about LHC. So we all know that 4th of July in 2012 we declared the results of discovery of Higgs boson, and it was made public on that day. And now I will show you another small video from from the Nobel Prize declaration in 2013, so this is partly a video when all the scientists from CERN who came together and they were watching this declaration of the result. And
this year's prize is about something very small that makes all the difference. The Royal Swedish Academy of Sciences has decided to award the 2013 Nobel Prize in Physics to Professor François Englert at Université Libre de Bruxelles, Belgique, and Professor Peter Higgs at University of Edinburgh, United Kingdom. And the Academy's citation runs for the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles, and which recently was confirmed through the discovery of the predicted fundamental particle by the Atlas and Sirius experiments at CERN's Large Hadron Collider.
So this video was actually to show you the excitements that you get after doing such experiments and after discovering something that is which is breakthrough in the history of physics. So now the question comes on how can you join. So let me be very honest about this. So pursuing a career in high energy physics is not very easy. It's very challenging at times, and you have to have a very good motivation and a very good passion for doing physics itself, because otherwise it is quite impossible to make to these large collaborations. You have to have a good academic qualifications to make to a good PhD program. So all these things are interconnected, and you have to cross several hurdles like doing your bachelor's, master's that you are right now involved into, and before you can join a good PhD position, maybe here or maybe abroad or wherever you get a chance, and then finally you can make it to a collaboration like LHC, or there are several other high energy or astrophysics, astroparticle collaborations which you can join. So you have to be very motivated and very passionate about what you are doing. And so if that is even not enough for you to get motivated, so here I have put some pictures of me, and these are basically from all around CERN and from Geneva itself, or maybe in Switzerland. So Switzerland is a beautiful place, so if that gives you enough motivation to do physics, then why not? So so that's basically it from me, and thank you very much, and I'm up for any sort of questions or doubts that you have.
Okay, thank you, Kyo, for the nice presentation. I think there is a breaking of voice. Students, is there any question? It is shortage of time, so we can take only one or two questions. Utti, can you see from this chat box?
Okay, yeah, I see that there are a lot of questions. Let me see.
So you can choose the important two questions, then we should proceed the next talk, last talk.
So one question that I can see, which I think is important to answer here, is that is CERN going to make a much bigger particle collider? Yeah, that's true. The work is already commissioned and people are already working in a larger collider, which is known as the Future Circular Collider, or FCC, and they will try to achieve an energy of 100 TeVs or something like that, and it would be 100 kilometers of circumference, so it is bigger than the present ring. And this if you remember the video that I showed you, so these smaller rings are basically producing so slowly accelerating the protons. So so once you have this accelerated protons in LHC, that can be further injected to a bigger ring, which we plan to make up next, and that is known as the Future Circular Collider. and then I see that there is a question about tips for college students who wants to be a particle physicist. So actually there are a lot of things. I mean, from my personal experience, I would say is that you have to have your basics very clear. By that, what I mean is you need to understand your course contents very well, like whatever your course is offering you in your bachelor's or master's level. So you have to have a very clear understanding about that, and based on that you go into even more higher studies like PhD or in MSc or in PhD. You learn those subjects more and more, and that sort of gives you more motivation of doing particle physics. And yeah, that's one tip that I would always give you, that make your basics very clear. That would be the fundamental block of doing pursuing any career in physics. Yeah, so I think those are the two main questions.